Hey everyone, thanks for tuning in to the last demo that I'll be doing for this fall 2023 class on deep Q networks. This is the second demo that we've done on reinforcement learning. To remind you, reinforcement learning is a very flexible and interesting framework that allows us to learn an environment by interacting with it. And this interaction and feedback cycle makes it different from the supervised learning settings that we're used to. But as you'll see, many of the same ideas that we use there will apply again. Of course, I'm most excited about these reinforcement learning demos because I get to play games in front of you. The particular game that we'll be trying to learn today, and then I'll play shortly, is called Lunar Lander. And the idea is that you are in a spaceship like this, and you're trying to land without falling to like your death in a way such as this. So I would like to say that that was because I was trying to talk, but really it's because I'm terrible at this game. I am trying to land in a particular location. I can press the actions I can take are pressing these thrusters, and then I get some reward from the landing process, which is how fast I came in. So to be formal in the reinforcement learning context, there's a particular state, which is the framework of the world at this moment. There are actions I can take, which are which one of these thrusters I'm pushing. And then the reward I get is like what happens in the next state, which is initially like I get some points for just staying alive. And then I also get some reward, the positive reward if I manage to land it, and the negative reward if I end up crashing, as I did just there. Okay, so that is the framework that we're trying to learn. There are states, there are actions, and there are rewards. Last time we talked about a policy gradient approach to this, where we formulated a like typical first attempt at solving this problem, which is that we looked at the expected rewards over time, and then we wanted to maximize those, which is really the same thing as minimizing the negative quantity of that. And that's what we did. Today, we'll be taking a different approach, which is using Q-learning. Q-learning, just to preface, is something that's been around for a while. This isn't particular to deep learning, but the idea of using a deep neural network for our Q function is particular to deep learning. So that's really the thing that's a more modern contribution to it as we've gotten larger and more powerful computers. But let's explain the idea of Q-learning. The idea is to get the long-term expected discounted reward of an action in a particular state. So it's not just looking one step ahead, what is the immediate reward I'm going to get? It's saying, what is the reward I'll get in the next step and in all the future steps if I take a particular action and then follow the optimal policy. If we had these values that told us like what is the value of this action in this state, then we could solve this problem really easily because the best policy is simply to take the action which maximizes the Q value in the current state. And then we could solve this problem. So on the lunar lander, we say, okay, if I fire the bottom thruster by this much at this particular state, then and that's the one with the largest Q value, then I'll follow that one, I'll get to another good state, and I'll keep following these Q values until I get to a final state, which if the Q values are good, will be a good state with good expected reward. Of course, the tricky part is getting these Q values. How do we get them? Well, we'll start by parameterizing a network, which we'll call our Q value network or deep Q network, DQN. And we'll randomly initialize it at first so that the Q values we're getting are completely meaningless. But our hope is that our Q values will eventually satisfy this Bellman equation, which is just a fancy term for a recurrent relationship, so that the Q value of a particular action in a particular state is the immediate reward I'm going to get, but also plus this other quantity which accounts for the future. I'm discounting this quantity because I want to prioritize the immediate rewards that are more certain. And the rest of this quantity is the maximum Q value that I could hope to get in this new state S prime. Our hope is that the Q values will eventually satisfy this equation. And if they do satisfy this equation, then our policy is easy because we'll just take the action which maximizes the Q value at every step. Really what differentiates this and what makes it unique is we're not just taking into account the immediate reward that we're going to get, but we're also taking into account all the future rewards. And that's the second term here that plays an important role. And the second term is also tricky because we're defining a Q value in terms of the Q value function, just at a different state, S prime and A prime. If you'd like more derivation of it, I strongly recommend that you check out Chinmay Hegde's fantastic notes, which this class is based on. And it's a 9-minute read and really a lovely introduction. But for now, that's all I'll say about that and the reason we're using Q values. With this hope for our Q values in mind, we will define a loss function. And the loss function is really the difference between the left-hand side of this equation and the right-hand side of this equation. And by defining our loss in this way, our hope is to equalize these two sides. So we'll get a Q value function which correctly outputs the actual value of a state in an action. And to do this, there's a complicated recurrent relationship because that depends on this Q value as well. We want this thing to be 0. So we'll square this or take the L1 loss, or just take the L1 norm, which is absolute value. If it's absolute value, it's discontinuous, or sorry, it's not differentiable at 0. So we'll just smooth it out sometimes. That's what we'll do today. But really, the particular way that you make this a positive quantity isn't so important. This is defined not just for a particular example of a state, action, reward in the next state, but an expectation over them. And that's why there's this expectation symbol right here. So we'll compute this loss for lots of different 4 tuples, S, A, R, and S prime. And the variables in the loss functions are the parameters of our deep neural network that approximates Q. So this is defined in some parameters, and the other place it appears is also defined in these parameters. Initially, our Q values will be meaningless, but if we update the values with the 4 tuples that we get from interacting with our environment, the Q value will become a meaningful metric of the quality of an action in a particular state. Apologize for all the scrolling. Okay, so there are several points to keep in mind. The first of these is that the Q value appears in 2 points in this loss function. That's an issue because if we're just trying to get these two to agree with each other, then that's a trivial problem if we can manipulate both of them, and that doesn't actually solve the problem that we're interested in. So what we're going to do is fix this second point so that we're going to detach this value from its gradient structure. So then when we go to optimize the loss function, we're only updating this network. Of course, we do want to improve this network over time, so we don't always want to keep it fixed. So every once in a while, we'll inherit the parameters from this Q value function that's learning, and we'll just put them into this one, but keep this one fixed during the learning process. And we'll update it occasionally. The second thing we'll do is that sometimes gradients are an issue, so we will clip them. This is equivalent to replacing the squared error loss here with the smoothed L1 loss, which is like absolute value. It's just nice and smooth around the origin. And then the other thing that we'll do, whereas before we optimized over a particular trajectory at a time, today we don't need a whole trajectory. We actually just need this 4 tuple. So what we're going to do is we're going to sample lots of trajectories following this approach and keep track of all of the 4 tuples that we observed along the way. Then we'll store this history in a DEQ or ND array called a replay buffer, which will query uniformly at random to extract samples, and then we'll optimize over these samples. So these are the practical considerations for Q-learning. With these in mind, let's jump right in. We'll have to install some specialized software. Every time I do this, it gets more complicated, and I'm always worried that it'll break, but this is currently running just fine. Hopefully by the next time that I go over this, not too much will break, and we can keep doing it. We'll import some libraries. The first thing we'll do is define this replay buffer. This is really the thing it's doing is keeping track of the actions that we take, the rewards that we get, the current state, and the next state that we get, and then whether we're done. We're going to store all of this information, and then we'll have a function for sampling a random selection of these. And then sometimes we will just update our pointer to overwrite things that we have at the beginning of the point. So we'll overwrite this when this gets too large, which is maybe I'm not actually sure if that's an option that we can right over this. This is just keeping track of the 4 tuples that we described earlier. We'll define our deep Q network. It won't be very deep. It'll be fairly simple, just 3 linear layers with ReLU activations. The input dimension will be the state and the dimension of the state and the dimension of the action that we want to represent. And then the output will just be a real value, which is the Q value, how valuable, or what is the expected long-term discounted reward of this state if we take this action and we follow the optimal policy here on out. We'll define all of this, again, using the wonderful Gymnasium environment for Lunar Lander. We'll specify the size of how much 4 tuples we'll keep around, the batch size, how often we'll update our second Q value function with the one that we've learned, and then the number of frames that we're sampling from. So the length of the Lunar Lander trajectory that we'll use, which will be frames of this environment. So we're at each particular state is a particular snapshot in time of where the lunar lander is, and then we'll take one step forward, and that'll be like taking a particular action on the controls of this lunar lander. We will put this on the GPU if possible, which I think is available. I think we're on the T4 GPU given for free by Google. Thank you very much. We'll get the observation dimension, the action dimension, and then we'll define this network. The network is, I think I misstated this. It'll be taking in the observation dimension, right? Yeah, sorry, this makes so much sense. The input is the observation, and then the output is the Q value of each one of the associated actions. So instead of learning, we simultaneously, we pass in a particular state, and then we look at what is the Q value for each one of the possible actions that we could take in this state, which is a more sample efficient way of the thing that I described earlier. We'll have a target network. This is the second place that the Q value appears in the loss function. And then we will load the weights from the target, from the DQN into the target network every time. And then we'll set this to evaluation. So we're not evaluating the gradient of it. We'll define our optimizer, which will only optimize over the parameters of the DQN. And then we keep track of this list. What are we doing with it? I'm not sure we're doing anything with it. That's funny. But I don't want to delete it for fear something will break. Okay. The first primitive that we'll implement is a select action procedure. The select action at a high level will take in the current state and it'll make some selection of an action, which is either random or selected according to the largest Q value. The reason we're interested in doing this randomly is because initially, before we've interacted with the environment at all, we don't know anything about it and we want to explore it. So if we take random actions, that will enable us to explore through the different space of this environment and learn like the different actions and states and everything else that's going on here. Eventually, over time, as we have a better Q value, as we trained our Q value for longer, we want to, instead of continuing to explore randomly, we'll transition to taking the action which has the highest Q value, and then hopefully we'll get to better and better states. This in our lunar lander game would correspond to staying afloat in the air longer and longer. And we control this trade-off with this epsilon parameter, which is some quantity between 0 and 1. If it's closer to 1, then that means that we will be more likely to take a random action. If it's closer to 0, we'll be more likely to take the action with the largest Q value. After we select our actions, we'll take that step in the environment, we'll get out the next state and the reward, and then we'll store this in our memory. This is the replay buffer class that we defined above. And then the second primitive or second function we need is computing the loss. The loss we will get from a particular observation or a sample, or we'll put all these samples, we'll get out their states, the next state, the action, the reward, and this done feature. These will all define, this is the 4 tuple that we need, the S, what we called before, the S, the A, the S prime, and then the R quantity here. We'll compute the right-hand side, or sorry, I guess this quantity here, Yeah, so we compute the current Q value, the next Q value, and then the target, the thing that we want our Q value function to be equal to, is this quantity, which is the reward times plus gamma times the next Q value, times this mask. This mask is just used so that we only look at examples that are not done yet. So if a game is ended, we don't want to look at those. We will put this on the device, and then the loss function is the difference between this quantity and the actual Q value. And then when we go to optimize this, we'll only be optimizing this, the place here where the Q value appears. We're going to use this function for nicely printing out the losses and scores as we go along, and then we'll train. We initialize our epsilon value to 1, so that we're initially taking lots of random actions. We define this discount factor, the observation dimension. We'll create a replay buffer. We'll put everything on the device, and then we'll get our current state. Then for the total number of frames that we're going to play, which I think we defined to a really large number up here, which is 40,000. So we're playing for 40,000 frames. We will select our action using this primitive. We will update the state to the next state and add this to our reward. If we're done, we've lost this game, we've gone off of in the game of Lunar Lander, we've crashed, or we've gone off of the screen, then we'll reset in our environment and append the score. If not, and we're ready to train, so we have enough things in our memory, they're above the batch size, then we'll create a sample from this, we'll compute our loss, and we'll do the backward pass and the optimization steps that we're used to, and then we'll decrease epsilon by a little bit. So every time we learn a better Q value function, we'll decrease the amount of epsilon that we're using, or we're decreasing the amount of time that we're taking random actions. And then we will every once in a while update our DQN target, the second place the Q value function appears, with everything we've learned for our first Q value function, DQN. And then we'll also plot this every once in a while so that we can visualize this process as we go. We'll define a similar function for testing. Here, we're just going to select our action by just following the Q value function. So we're just taking the 0 action, and then we'll get our next state and update our reward, and we'll keep track of all these frames as we go so that we can watch a nice video of our learning process. Before we train, let's watch this process. Notice that this is a 1 second long video, it's really fast. If we play it, in the top, you can see the lunar lander come into view and then immediately zip out of the frame. So it looks like we've done some random exploration as you'd expect, and we're hitting all the thrusters, and because we're hitting all the thrusters, it zooms out of view and the game's immediately over. So our goal is to train a Q learning function, which will give good Q values, and when we follow them, we'll get a nice policy, which will be longer than a second. That's our hope. We do this training process. The score, of course, oscillates randomly over time because this is a very sparse reward framework. Like, we only get large reward, positive reward if we land here, and we only get large negative reward if we crash or end up out of view. And then we can plot our decreasing epsilon value over time. We will test this and test the trained environment, and then we can visualize this movie. This is 20 seconds long, which is already very impressive. And it looks like the function has learned what a good policy, at least to stay in air. So it's remarkably stable, it's staying in the same place, it's slowly decreasing over time. I would say that this policy has learned how to operate this lunar lander quite well. We'll see if it's able to land, and it's not. The amount of time that we gave it ended before we, maybe let's reconnect real quick and see if we can sample another fragment from this. Will this run? No way. I'm gonna give this an error because we disconnected. Or it might work. Oh my gosh, cool. So let's make another video of this other attempt. Like before, it's 20 seconds long, so this you can see is a different environment. It's kind of doing the same thing where it like hovers a little off to the right. I have low hopes for whether it'll actually be able to land correctly, but I am very impressed that it's able to stay in the air so long. So we'll get it go. Aw, cool. So it did manage to land, just not at the right spot. So I guess it's learned control, but it hasn't figured out that it needs to land between these two flags. Amazing. So this is all I have to talk about Q-learning today. If you want more details, I strongly recommend you read Chinmay's lecture notes and reach out if you have any questions. Thank you so much for watching these videos. I've greatly enjoyed making them, and I appreciate your time. All the best.